So welcome everyone. Welcome to these sessions. And from today, basically, I'm starting 48 live classes sessions. So in next 2 months, in 60 days, I am going to have 48 live classes. In these 48 live classes, we will have the two goals. Number one goal will be, or I would say three goals. Number one goal will be Part C syllabus coverage. So every time we begin this session, we begin at 6 p.m. and at 6 p.m. we are going to begin with Part C syllabus. So from 6 to 7 or 7:30 p.m., we are going to cover some topic of Part C syllabus, which is obviously a difficult topic, but I will try to make it as simple as possible. And I will teach you the concepts as well as the part portion or the formulas which are required for the exam point of view. So both of them will be covered, concept as well as exam point of view. And you will be able to solve the previous year problems after watching these lectures. And I will be covering each and every previous year question of Part C in my lectures itself. So all of your previous year questions will be covered, at least 90% of it. Some questions I will leave if they are not important, or if there are something wrong with them or something. 90% we will cover it up in the classes as such. After our Part C is done, then our second part of the lecture, so there will be 15 to 20 minutes break between that. So once our this 1 and 1 hour half our lecture finishes, you will get 15 to 20 minutes break. And then after that break, we will begin with the Part B revision. So first part of the session will be Part C, and the second part of the session will be Part B. Part B, I'm not going to cover as a lecture because you already have all the recorded lectures. So if you are a part of my course, you already have a full-fledged Part B recorded classes for all the topics. But since we don't have time to cover all those classes, what I am going to do is I am going to do the revision of those classes. So I am going to take 48 revision classes. And in each revision classes, the idea will be very simple. Revise the formulas, revise the previous year questions, and that's all. Previous year question revision plus important questions plus concepts and formula done. And in the end of this session, we will have some time for doubts or for some solving of Part A questions, maybe on some days. On some days, it will be doubts. So the 3-step things will be followed right now. Okay. So that is going to be our goal. Any doubt as such? Yeah. Okay. So this is how the things will proceed. Today's topic, I have deliberately taken it as a difficult topic. Waveguide is something which is considered to be difficult as such, but it's not as a lot of difficulties there in this. But yes, students find it difficult to cover it by themselves. So for waveguide, what I'm going to do, so first of all, this week we are going to cover electromagnetism. In revision also and in Part C also, we are going to cover electromagnetism because I felt that students thinks that electromagnetism is a difficult subject. So I want to make this subject simpler for everyone so that I can basically you can score very good marks in this subject. Okay. So our idea will be to do the electromagnetism this week. Okay, fine. So let's now begin with our topic. So in electromagnetism, there are basically 4 topics. 1, 2, 3, 4 topics in Part C. In Part B, there are many topics, but in Part C, there are 4 topics. One of them is waveguides. Second is potential formulation. Third is radiations. And fourth is relativistic EMT. I will cover all of 4, and I will be covering each of these 4 topics. And I will do all the PYQs. I will give you all the concepts. I will give you all the formulas as such required. Our today's goal is to go for waveguides. Okay. So with this said, I want to start my topic, which is waveguides. Okay. So I hope everyone is clear with the plan now. सबको प्लान जो है वो एकदम क्रिस्टल क्लियर हो गया है. 48 क्लासेस में हम अपना CSIR नेट का बड़ा सा सिलेबस को एकदम छोटा सा करने वाले हैं. अब स्टार्ट करते हैं अपना पहला टॉपिक, विच इज वेवगाइड. चलो. As the word suggests, waveguides. Waveguide is a physical structure. It is some sort of a physical structure which is used to guide the electromagnetic wave. What are electromagnetic waves? radio waves, microwaves, light waves from one point to another without any energy loss or with minimum energy loss. So let's say I want to guide my electromagnetic wave from one point of the earth or one point of the room to another point. So from point A to point B, I want to send my electromagnetic wave. One idea is to just send it directly. Why you need waveguide? You just directly send it, or you send it through the satellite. Why do I need waveguide? If I directly send my electromagnetic wave, let's say I directly send my electromagnetic, then as it is moving, the energy loss is happening. We are not protecting our electromagnetic wave. The energy of electromagnetic waves keeps on getting lost. So फ्री स्पेस में क्या प्रॉब्लम आता है कि इलेक्ट्रोमैग्नेटिक वेव के अंदर एनर्जी लॉस बहुत ज्यादा हो जाता है. इफ यू अगर आप कोशिश करो एक साइड से दूसरी साइड वेव को गाइड करने का, एनर्जी लॉस हो जाएगा. Another idea is that okay, let's try to do satellite communication, right? Satellite communication. तो आप क्या करो, satellite communication कर सकते हैं. But the problem with satellite communication is that first of all, it cannot be used for all the waves. For very particular waves, it can be used. And secondly, you have to protect your wave first. You have to protect your wave first. You encapsulate the wave. This is known as wave encapsulation you do. And then there is a filtering and a lot of processes are involved. You do a electronic processes on your signal और फिर जाकर आप जो है communication कर पाते. So it's a very big problem. Okay, sending the electromagnetic energy from one place to another is a big problem, and it is one of the most important branch of engineering. Okay, waveguide is a very important discovery in this context. For example, our internet is working on optical fibers. So we are getting the internet signals from optical fibers, and optical fiber is a type of a waveguide. Similarly, there are other waveguides as well, and we are going to study one of them, one waveguide out of all the examples. Okay, so when someone asks you what is waveguide, you can say that it is a physical structure which helps us to guide electromagnetic wave from one point to another without or very minimum energy loss. Very minimum energy loss. And what are the waves we can transfer from one place to another? Radio waves, microwaves, light waves, and so on. There are different types of waveguides. For example, hollow tubes, pipe, simply pipe. Hollow tubes also behave as if they can also become a waveguide. So the simplest waveguide is hollow pipe. Hollow pipe is basically just a pipe, metallic pipe. That's all. That's all. And that's a waveguide. Another is dielectric filled, means the pipe is not empty, but some insulating material is filled in it. For example, mica, some organic liquid, inorganic liquids. So inside the pipe, some liquid is filled or some insulating material is filled. That becomes dielectric filled. Then optical fibers, as you know, is used for internet communication. That is also one of the waveguide. So these are some of the examples of waveguide. And waveguides are divided in terms of frequency range. Means if you want to send radio waves, you will use one kind of waveguide. If you want to send microwaves, you will use other kind of waveguide. And if you want to send light waves, you will send other kind of waveguide, right? And also it depends upon the applications. Is it a medical applications, communication applications? What kind of applications do you have or in your mind? So on the basis of these two things, we categorize our waveguides. In our syllabus, a very small part of waveguide is there. We don't have to study all the kinds of waveguide. We only have to study the hollow waveguides. That's all. Hollow tubes. And that is one of the simplest waveguides you can ever study. So we only need hollow tubes. All the questions that have came so far in CSIR net are only based on the hollow tubes. Nothing else have came so far in a CSIR net exam. Okay. So I'm going to begin with the hollow pipe waveguide. Okay. And that is going to be one of our major topic for today. Okay. So what is hollow pipe waveguide? So You have to first of all consider some hollow pipe. तो एक hollow pipe assume कर लो, आपके पास एक hollow pipe है, खाली pipe, अंदर से एकदम खाली. And let's say there is an EM wave. तो इसके अंदर now let's send an EM wave, and EM wave is confined to move inside this waveguide. You have one waveguide, अंदर से खाली, it is empty from inside, and you have an electromagnetic wave जो इसके अंदर जा रहा है, and electromagnetic wave is confined in this wave. Confined का मतलब होता है it has to stay inside. It is inside. Okay. Now you can ask me that what are the properties of these waveguides? कैसा दिखता है? What is it? क्या है इसके अंदर? So I will say waveguide is a perfect conductor. ये जो pipe है, this is a perfect conductor. So this is an example. You can see here, this is a pipe and this is a perfect conducting pipe. And since it is a conductor, electric field and magnetic field is zero within the material, not inside the material. यहाँ पर फर्क समझना बड़ा जरूरी है. I am saying that within the material, electric field and magnetic field is zero. What is within the material? You see that this material has some thickness. You see this thickness, this small thickness. Within this thickness, let's say you have a glass, steel glass in which we drink the water. Now, steel glass has some thickness. Small thickness of the steel glass is there. I'm talking about that thickness. Within that material, electric field is zero, and within that material, magnetic field is zero. It does not mean that inside also electric field and magnetic field is zero. In the empty space, बीच में जो खाली जगह है, वहां पर इलेक्ट्रिक फील्ड है, वहां पर मैग्नेटिक फील्ड है, क्योंकि ईएम वेव वहीं तो ट्रेवल कर रही है. ये जो बीच में वी हैव एन एम्प्टी स्पेस, इन दिस स्पेस ओनली इलेक्ट्रोमैग्नेटिक वेव इज मूविंग. So electric field and magnetic field is not zero inside. It is zero within this material, this material. Within this material, electric field is zero and magnetic field is zero. Okay. Yes, pipe can have any shape, but in our syllabus we have a rectangular pipe. We will be doing the problems with the rectangular pipe, but yes, pipe can be made up of any shape. Okay. So let's, with this said, yes, it will affect everything. It will affect the signal frequency range and everything. Yeah. Then we have a boundary conditions. Okay. So first thing we learned, it's a perfect conductor. Second thing we learned is magnetic field and electric field is zero within the material. So at this point, electric field and magnetic field will be zero. At this point also, electric field and magnetic field will be zero. At this point also, electric field and magnetic field will be zero. Then we say that we have to follow some boundary conditions. And this is a knowledge I'm taking from the electrostatics. If you don't know this knowledge yet, don't worry. We are going to revise these boundary conditions as well. For now, take my words. Take my words. Okay. So let me give you an example. For example, let's say this is a metal. This metal has some thickness. This metal has some thickness. Some thickness of the metal is there. Okay. So let me make like this. This is a metal and this metal has some thickness. Within this metal, electric field is zero and magnetic field is also zero. Okay. And now one very important boundary condition is that parallel component of the electric field has to be continuous and perpendicular component of magnetic field has to be continuous. So if I talk about this boundary, this boundary, okay, there will be some electric field below this boundary and there will be some electric field above this boundary. And electric field can be parallel to the surface or it can be perpendicular to the surface. I am interested in the parallel component, this component. The component which is parallel to the to the plane, to the boundary. So there is some electric field below the boundary and there is some electric field above the boundary. Now what happens is above the boundary electric field is zero, because above the boundary means you are inside the material, you are inside the conductor. So let's say this is a conductor and this is my electric field. This conductor has some thickness and this is my boundary. Above this boundary is my hand, so electric field here is zero. And as a result, electric field here will also be zero. Why? Because electric field has to be continuous. Whatever is the value below has to be the value above. Above the boundary, I have my hand, and in my hand, electric field is zero. So below my hand, electric field should also be zero. Which electric field? Parallel component of electric field. Parallel to what? Parallel to my hand. So this electric field will be zero, but this electric field will not be zero, because this electric field is perpendicular to my hand or my conductor. But this electric field is parallel to my conductor. So we are happy. We say that, okay, inside the material, on inner wall, parallel component of electric field is zero. The same boundary condition is for the perpendicular component of magnetic field. So for magnetic field, it happens reverse. Magnetic field के लिए उल्टा होता है. This magnetic field is zero. Perpendicular component will be zero. Why? Because above the boundary, electric field and magnetic field both are zero. So above the boundary, magnetic field is zero. So below the boundary also, magnetic field should be zero. Why? Which magnetic field should be zero? Perpendicular magnetic. Not this, but this. So these are our two boundary conditions. First, parallel electric field is zero and perpendicular magnetic field is zero on this surface. On this surface. That's all. So these are the two boundary conditions. In order to satisfy these boundary conditions, what happens is that some charges are induced and some currents are induced on this conductor surface. I need to make sure that these boundary conditions are 110% satisfied. If I want to make sure that this has to be satisfied, then in order to satisfy that, what happens is that on this conductor itself, surface of the conductor, some charges appears, which is known as the induced charges, and some current also appear, which is known as the induced currents. Let me give you an imaginative picture for this, that why charges comes when we have to satisfy the boundary conditions. For example, let's say I have this positive charge and I have this conductor. Okay. Now you also know that when you place a positive Q, plus Q, and there is a conductor outside, here we will have minus Q, and here we will have plus Q. But the question arises that why do we get this minus Q and why do we get this plus Q? What is the need? Why these charges got induced? So the answer lies like this. So let's say this was your sphere. This sphere had some thickness. I'm just showing this thickness with the yellow color so that you can imagine the thickness. Every conductor has some thickness. This boundary will have some thickness. Right? So let's say this yellow part is a thickness. Now you also know that inside the conductor, electric field should be zero. And if electric field should be zero, then charge inside this should also be zero. That is why if you have plus Q, you also need minus Q here. So that plus Q and minus Q becomes charge zero and hence electric field zero. When I will teach you or revise the Gauss law, you will get much better idea. But right now, I just want to show you that sometimes to satisfy the boundary conditions, charges appear on the surface and also current appears on the surface. So this is also very important line for us. This tells us the physics. ये हमें physics सिखाता है कि बाउंड्री कंडीशंस को सेटिस्फाई करने के लिए सरफेसेस पे चार्ज और करंट्स अपेयर हो जाते हैं, और इस केस में भी अपेयर होंगे. They will get appear in this case as well. So this was a summary or brief about our hollow pipe. So we took a pipe. Pipe is made up of a conductor. Within the material of a conductor, electric field and magnetic field is zero. Then there are two boundary conditions. One of them is the E parallel has to be zero and B perpendicular has to be zero. And in order to satisfy these boundary conditions, our surface will have some free charges and it will have some free currents. Great. Next part. Now our wave pipe is, sorry, our hollow pipe is ready. So let's send the EM waves. So now I am sending the EM waves. So these are my EM waves. So this is my EM wave. Electromagnetic wave has two things. oscillating electric field, oscillating magnetic field. And this is your electric field and this is your magnetic field. This thing tells you that wave is sinusoidal, oscillating. It's a plane wave. Plane wave means it's oscillating like a sine wave. This thing tells you that, because you also know that e raised power iota theta is cos theta plus iota sin theta, but we will not go in the maths. This thing tells you that your wave is a sine wave or a cos wave or a mixture of both. Basically, it's a harmonic wave, perfectly going wave. This thing is an amplitude of this wave. Sometimes this amplitude is constant. When it is a constant, we call it as plane wave. Sometimes it is not constant. It depends upon x and y. For example, if the wave is moving forward, the amplitude can change. Like, for example, in standing waves, this happen. Or in waveguides also, this can happen. This can happen. I'm not saying for sure, but we don't know yet. So electric field, in this case, however, remains constant. Okay. So E naught in our case will remain constant, but E naught can change. But in waveguides, it does not change. You see here, amplitude is not changing. So you see, first time also the wave achieved the maximum height. Second time also the same maximum height. Third time also the same maximum height. So every time the amplitude is same. Amplitude means maximum height or maximum depth.
Sir,
Yeah, please. Yeah.
sir, is the amplitude not changing because the pipe dimensions are fixed?
Pipe's dimensions are fixed. Yes, yes. If we take some randomly shaped pipe, then yes, it can change. Right now, we are taking a symmetric kind of pipe. Okay. So I will explain further, but what is the exactly pipe what we are taking. But yes, you are right. Okay. So we have a pipe, and now inside that wave is going like this, and amplitude of those waves are not changing. So E naught is more or less not changing, B naught is more or less not changing, but it does not mean that they cannot change. They can change. They can change. Okay. And we will study that if it is not changing or not changing or not changing. So Kumaran has said that it's a conductor, but why it is not decaying? So there is a difference. One thing is that you are moving inside a conductor. No, my wave is moving in a free space, in a hollow space. In this, I'm not moving in a conductor. I'm surrounded by a conductor. My boundaries are made up of conductor, but I'm not moving in a conductor. You have to understand this difference. Whenever the wave moves in a conductor, its amplitude decreases exponentially. Amplitude कम होता जाता है, कम होता जाता है, कम होता है. So wave will go like this. खत्म. Finally खत्म. But in this case, my wave is not moving in a conductor. Wave is moving in a free space. Hollow pipe है ना, अंदर हवा है. Inside there is an air, so my wave is traveling in that air. But yes, my wave is surrounded by the boundaries. Yes, there is a complete vacuum inside a pipe. Complete vacuum. Okay. Okay. Great. So we have electric field, we have a magnetic. Electric field and magnetic field can change with time, and that is okay. It changes with time. In fact, it changes with time. Okay. Now you know that in any electric field and magnetic field has to satisfy four conditions, four equations, which are known as the Maxwell equations. And four Maxwell equations are del dot E equals to 0. Del dot E in reality is known as rho by epsilon. But since there are no free charges, I'm not putting any free charges anywhere. I'm not going and putting some free charges. So rho is 0, so del dot E becomes 0. Del cross E is minus curly B by curly T, which is known as a Faraday's law. This is known as a Gauss law. And then we have del dot B equals to 0. Del dot B says that net magnetic flux is 0. When we will revise EM waves, we will talk more about this. And then there is the last equation, del cross B equals to 1 by C square, curly E by curly T. You might have seen equation something like this. Del cross B equals to nu naught J plus nu naught epsilon naught curly E by curly T. There is no free current. It's a hollow pipe. There is no free current. So this is also 0. And nu naught epsilon naught can be written as 1 by c square, because c is given by 1 by nu naught c epsilon naught. That is why nu naught epsilon naught can be written as 1 by c square. So that is how you get your fourth equation. That is known as the Ampere's law. So we have 4 equations, and our electric field and magnetic field has to satisfy these 4 equations. Okay, it is necessary. Our main idea is to find this E naught and B naught. What is this E naught and what is this B naught? Okay, inside the waveguide. So our main objective is to find this E naught and B naught, which are the amplitudes. And we have to keep 2 things in mind. First of all, our electric field and magnetic field should satisfy this Maxwell equation. Perfect. And it should also satisfy these boundary conditions. Perfect. First of all, we assume that, let's say our electric field and magnetic field is something like this. Now you tell me that what will be the value of this E naught and B naught. Do your mathematics and tell me. When I am doing my mathematics, I will not show you the mathematics, because that's not important for us. When we are doing the mathematics, 2 things are important for us. One is that they follow the Maxwell equation. Second, they also obey the boundary conditions. If both of them are satisfied, then we can get our E naught and B naught. That's all. And none other than this is fundamental to us. If we break any other law, it's okay, as long as we are not breaking these 2 laws. First, Maxwell equation. Second, boundary conditions. Anything else we can break, we don't care. And in fact, we break a very fundamental law of EM wave, and that law is very, very fundamental. Let me explain what did we break. When you learn EM wave first time in class 11th, remember, EM wave is a transverse wave. So our teachers say that EM wave is a transverse wave. What is this transverse wave means? Transverse wave means that electric field is perpendicular to magnetic field, and they are also perpendicular to the direction of the wave. So let's say the wave is going along x-axis, then electric field is along y-axis, and magnetic field is along z-axis. So this is in the direction in which the wave is going. Let's say this is in the direction in which wave is going. Then this is the electric field and this is the magnetic field. All 3 are perpendicular to each other. This is known as transverse wave. But now, as a matter of fact, if your wave is inside the waveguide, then your wave no longer remains transverse. Now your electromagnetic wave is no longer transverse. Now the angle between electric field and wave is not 90 degree. Now the angle between magnetic field and wave is not 90 degree. That is one of the very fundamental. Yeah, please.
Excuse me, sir.
Yeah.
Sir, initially there was no free charge or current inside the conductor.
Yes.
I mean, within the conductor. So
Yes.
the Maxwell's equations were getting satisfied. But then earlier you said that for satisfying the boundary conditions, free charges or current might appear in the conductor.
No,
so then the Maxwell's equations.
I said charges and currents has to come. Those are bound charges and bound currents, not free charges and free currents.
Okay, sir.
There are 2 types of charges which can be there. One is bound charges, like polarization, and one is free charges. So the charges which will be induced will be bound, not free. Okay.
Okay. Okay, sir.
Yeah. Okay. So now, main concept we say is that electromagnetic waves in free space are transverse. When the electromagnetic waves are moving in free space, they are transverse. Electric field perpendicular to wave, magnetic field perpendicular to wave, and all of 3 are perpendicular to each other. But electromagnetic waves confined in the waveguides, when the electromagnetic waves moves in any confined area, moves in some sort of waveguides, then they are no longer transverse. Out of the box. Because we have to make sure that our boundary conditions are satisfied and our Maxwell equations are satisfied. And we cannot do that without making it not transverse. It is definitely non-transverse. They also have some longitudinal component. right? It does. So Shriya has a very good question that inside we have a free space, but yes, we have a free space, but we also have boundary conditions, right? If it was just free space, then there was no boundary conditions. Now it is moving in a free space, but we also have a boundary conditions, and that is biggest problem. Okay. So now we cannot say that electric field is perpendicular to magnetic field or magnetic field is perpendicular to wave. That is one of the fundamental law we broke here. And it's not something which physics is broken. Our Maxwell equations is satisfied, boundary conditions still satisfied, so it's okay. I'm happy. Okay, but this is new. This is very, very new. You have never seen something like that before. Okay. So now let's assume that one direction in which wave is going. So let's say the wave is going along z-axis, right? And it makes sense. The wave will enter from here and it will leave from here. So let's say the wave is moving along z-axis. Okay. So now our electric field will also have some z component. If it was moving in free space, then there was no z component. For example, if the electric wave is moving along z-axis, then electric field will be along x or y. It cannot be along z. But now we have no restriction. Our electric field will also have some component in the direction of wave. अभी तक मैं बोल रहा था कि इलेक्ट्रिक फील्ड हमेशा डायरेक्शन ऑफ वेव के परपेंडिकुलर होती है. This is something we learned in our 6-7 years of physics. But now I'm saying that no, it's not important. Electric field can also be in the direction of wave. So we can also have a z component of electric field and we can also have a z component of magnetic field. So the z components are basically known as a longitudinal components. These are known as a longitudinal. Longitudinal means the same direction in which the wave is going. So wave is going along z-axis. So these z components are known as the longitudinal components. Perfect. I'm happy. I'm happy. If you have any question, let me know. This much is the concept. Then some mathematics start coming up. Without boring you with that mathematics, you don't have to remember this. No need to remember this. Just showing you so that when I'm doing the mathematics, you at least know that how I'm doing the things. So this is known as the extracting the information from a derivation without doing the complete derivation. Okay. So now let's solve our Maxwell equation. So and use the boundary conditions. So let's say someone else solved the Maxwell equation, someone else used the boundary conditions, and they found out these 4 things. When they did the calculation, they came out with these 4 things. Let's carefully look at these 4 equations. First equation is a formula to find Ex, because electric field has 3 things: Ex, Ey, Ez, Bx, By, Bz. So basically we need to find 6 things. First formula is to find Ex. Second formula is to find Ey. Third formula is to find Bx, and fourth formula is to find By. We can find 4 things from these 4 formulas. As a matter of fact, if I just know Ez and Bz, Ez and Bz, Ez and Bz, Ez and Bz, if I just know Ez and Bz, only these 2. If I know Ez and if I know Bz, means longitudinal components, then I can find all other 4. There were total 6 things to find. But as a matter of fact, if I know only Ez and Bz, then I can find Ex also, I can find Ey also, I can find Bx also, and I can find By also. So how many degrees of freedom my system has? Anyone? How many degrees of freedom my system has? 6 or 2? How many variables my system has? 6 or 2? Only 2.
2.
My system has only 2 variables. One is Ez and one is Bz. Once I know Ez and Bz, that's it, complete. I get all 6. That's a victory. That's a victory, right? So the only problem I have in my hand is to find this Ez and Bz. So I just want to know this longitudinal components Ez and Bz. So there are 2 equations, and this is the first 2 equations you need to remember. So this is exactly you need to remember. So I will give you a 10 seconds to note these equations down so that you get a feeling of it. So please note these equations down. In order to find Ez and Bz, we need to solve this equation. First equation gives you Ez, second equation gives you Bz. If you solve these two equations, you basically get Ez and Bz. So if someone asks you to find all the 6 components, first step will be to find Ez and Bz, and then you can find Ex, Ey, By, Bz. That's all. By, Bx. So these two equations gives you Ey and Ez and Bz, longitudinal components. Okay. Now we will never solve this in our syllabus. We will never solve this. We will solve this, but not as extensive. We will solve this for only one example. Our main purpose is not to solve this for all the examples, but these are the two equations. Now we categorize them into 3 categories. Our waves can be categorized into 3 types. One is known as TE wave, which is known as transverse electric wave. तो 3 कैटेगरीज में हम अपनी वेव्स को नाउ डिवाइड कर सकते हैं, सो दैट आई एक्चुअली नो कि मुझे क्या सॉल्व करना. नाउ आई विल सॉल्व 3 केसेस. वन ऑफ देम इज ट्रांसवर्स इलेक्ट्रिक केस, टीई केस. आपने सुना होगा टीई वेवगाइड, टीई मोड्स, टीएम मोड्स, ये सब आपने वर्ड सुने होंगे. नाउ आई विल मेक दिस वर्ड सिंपल फॉर यू. So very first thing that you need to do is to find, first thing is TE waves, transverse electric. If electric field is transverse, then its longitudinal component will be 0. Make sense? If electric field is transverse, then its longitudinal component has to be 0. So whenever your Ez is 0, we call that wave as transverse electric. Ez is 0, but Bz is not 0. Similarly, transverse magnetic. So if your magnetic field is transverse, means perpendicular, then your longitudinal magnetic field will be 0. So whenever Bz is 0, we call that as transverse magnetic. Bz is 0, but Ez is not 0. And then comes TEM waves, transverse electric magnetic. When both of them are transverse, then Ez and Bz, both of them are 0. And there is a proof which you can look in Griffith's book, but the main statement says that TEM waves cannot occur in hollow waveguides. As long as you have a hollow waveguide, you can never have TEM wave. TEM wave is not possible. Either TE wave will be possible or TM wave will be possible, but TEM wave will not be possible. Okay. Now, any doubts till this point? Any doubts as such? Now, we need to solve this equation. Whenever we need to solve this equation, first thing we need to do is to specify our system. पहले तो बताओ ना system क्या है? We have a waveguide. Tell us the shape of the waveguide. What is the shape? So in our syllabus, there is only one shape, and that is a rectangular hollow pipe. That's all. First of all, in all the waveguides, only one waveguide is there, which is hollow. And in hollow also, there is only one shape, which is rectangle. That's all. So you only need to study rectangular hollow pipes. So now we have a rectangular pipe. So I can show you this rectangular pipe. This is our x-axis, this is our y-axis, and this is our z-axis. The wave is going along z-axis. The dimension along x-axis is A, and the dimension along y-axis is B. So you can say length is A and breadth is B. Okay. So we are solving for TE waves. TE waves means transverse electric. So if electric field is transverse, then its Z component will be 0, or you can say the longitudinal component will be 0. In physics, either you are in quantum mechanics, or if you are in electromagnetism, if you are in classical mechanics, the most fundamental tool of any physics person is separation of variables. So let's say you need to find some parameter. For example, here, if Ez is 0, then only thing that is left to find is Bz. Because you know, you need to find 6 things: Ex, Ey, Ez, Bx, By, Bz. If you know Ez and Bz, you know all other 4 as well. So only 2 things to find: Ez and Bz. Ez is already 0, gone. So only thing left to find is Bz. Now Bz is a function of x also, and it is a function of y also. So Bz will depend upon x also, and Bz will also depend upon y also. Here we use a separation of variable method. We say that Bz has some x part and Bz has some y part. For example, let's say cos x into cos y. So the final Bz has some x part and it has some y part. You also remember from the wave functions of two-dimensional wells, sine n pi x by a into sine n pi y by a. You remember all of this, right? If yes, let me know in comments, chat. So x component is separate, y is separate. This is known as the separation of variables. So I say that, so what I'm saying here is that my Bz is made up of two components. One component is only a function of x. Other component is only a function of y. So I can write my Bz as x comma x, which is a function of small x, and y, which is a function of small y. Now this can be anything. This can be cos x, sin x, tan x. That is exactly what I have to find. That what is this? And similarly, this thing will be a function of y. It can be anything. Sin y, cos y, tan y, e raised to power y. That exactly I have to find that what is this thing. But there will be two things. Bz is not a function of z. Bz is not a function of z. All of that comes through the Maxwell equations. Bz, if Bz is a function of x, it means as the wave is going further, the wave itself is changing. Your wave is moving along z. So if wave is going further, wave is changing. That cannot happen. Yeah, if wave goes up or wave goes along y, then wave can change. Okay, so it is not a function of z. Bz is a function of x and y. Okay. So now let's do the maths. Now you need to do the maths. And this is a maths that is important for you. Yeah, please.
Sir, can you explain this once more that why
Yeah,
Vz is a
why
function of
Bz
x
is
and
not
y?
a function of why it is only a function of x and y. Okay.
Yes, sir.
Okay. Okay. Let's try to understand this. How do you write your wave going along z-axis? In general, you write some constant and you say e raised to power iota kz minus omega. Now we want to find this e naught, this e naught. And this e naught does not depends upon z, it depends upon x and y. And why I'm saying that? Why I'm saying that? Because you see, so x and y, what does it mean? So my wave is going along this direction. My wave is going along this direction. If I am in the center of the, so this is my waveguide. If I'm in the center of the waveguide, then it is possible that my wave is something else. And if I'm close to the boundary, then it is possible that my wave is something else. So one wave is going here, one wave is going here, one wave is going here, one wave is here, one wave is here. So let's say this is my waveguide. So if my wave is here, then it will be something else. Amplitude of the wave here can be something else. Amplitude of the wave here can be something else. Amplitude of the waves here can be something else. So it is like the million of waves going inside. In this waveguide, millions of waves are going in. And if the wave is here, then the amplitude is something else. If the wave is here, amplitude is something else. But let's say the wave start changing with z. So as you're moving further, your waves are changing. So some wave entered, and as you're moving with z, the amplitude is changing. That is exactly that you don't want. Amplitude change means energy change. So let's say you send a wave with 20 energy. And as it is moving to z-axis, amplitude is changing. So energy is changing. Now you know energy cannot increase, but it can decrease. So it will result in energy loss. So our waveguides are designed in such a way, or mathematics also proves that wave cannot change with the z. Otherwise, as you're moving in the wave, your electric field and magnetic field are changing. Your wave is changing. And that is exactly that we don't want. Yes, you are close to the boundary, wave is something else. You are in the middle of the waveguide, wave is something else. But as you are moving forward in the wave, so let's say one person is running. So this is a waveguide, and one person is running in the middle. One person is running in the bottom. One person is running on the top. One person is running on the left. One person is running on the right. The speed of all this person can be different. Let's say speed is amplitude, or energy can be different. So energy of all these people are different. So middle person has energy 100. The top person has energy 0, because at the boundaries it has to be 0. In the bottom also it can be 0. And let's say at right it is 10, at left it is 20. So every person has a different energy. So energy depends upon x, y. But if the person is running and it is losing the energy as it is running, that is not allowed, right? We don't want to lose the energy of our wave. What do you say? What do you say? Right? Okay, clear? So that is why all the waves can make an interference. Interference happens when the same wave reflects. So we have to, what we basically have to do is divide the amplitude of single wave. It's not like that you are doing an interference of two separate waves, okay, and they both are going in same direction. You never
Sir,
get one perfect wave, right? Please, yeah.
so that
That
like we earlier saw that depends on X, Y, and Z. Then
B not
we
B not
like where
depends
is
upon,
the
yeah.
amplitude of
No. Okay, sorry. So okay, let me remove the
like it has
doubt.
three components, BX, BY, and BZ.
Okay, I get you, right. I get you. So I get your confusion. So your magnetic field is have three components: Bx, By, Bz. I am saying that this Bx depends upon xy, this By also depends upon xy, and this Bz also depends upon xy. You understand the difference? Xy. I'm not. So let's say you have a field. So this is a very basic knowledge actually. This is a field. Let's say I ask you to define Bx everywhere. I say, okay, at all the points define Bx. So you say Bx at this point is 20, Bx at this point is 10, Bx at this point is 10, Bx at this point is 20. So you see Bx depends upon X and Y. If you're here, then something else. If you're here, something else. So Bx is depending upon X and Y, where you are. But what does Bx means? Bx means the magnetic field which is pointing along x-axis. So yes, this is also Bx, this is also Bx, this is also Bx, this is also Bx. All four are Bx. But the value of this Bx depends upon X and Y. Right? You get my idea?
Strength is different at that direction at every point. Strength of BX.
Yes, the
Like
strength of the
it's
Bx is different at different XY values, right? Right.
so,
What do you say? Right. But it is Bx. Right? Similarly, we have By. By is also dependent upon X and Y. Bz is also dependent on X and Y. And we are finding Bz. Right. And Bz basically depends upon X and Y. So the value of Bz here will be something else, here will be something else, here will be something else, here will be something else. And it depends upon X and Y. Right. So that is what I'm saying. So Bz depends upon, one is X component and one is Y component. Yeah. Still any doubt, please let me. Yeah. Any doubt as such? Should I move forward? Clear everyone? Clear
सर
everyone?
BX मतलब क्या वो X के अलाउंग ऑसिलेट कर रहा है सर
ये वाला चीज ना, ये Bx पूछ रहे हो ना? यस, मैग्नेटिक फील्ड ऑसिलेट कर रही है
यस
और
सर
उसकी डायरेक्शन एक्स की तरफ।
ओके
मैग्नेटिक फील्ड
और
इज ऑसिलेटिंग। बी वाई का मतलब है कि वो वाई की तरफ ऑसिलेट, बी जेड का मतलब है कि वो जेड की तरफ ऑसिलेट। किसी भी बी एक वेक्टर,
ओके सर
बी मैग्नेटिक फील्ड एक वेक्टर, राइट? एक वेक्टर, ये दिस इज माय मैग्नेट। अब इसका कुछ एक्स कंपोनेंट भी होगा, इसका कुछ वाई कंपोनेंट भी होगा, इसका कुछ जेड कंपोनेंट भी होगा, isn't it? Every vector has three components. So that is what bx, by, bz means. अगर आपको इसका z कंपोनेंट मिल जाता है तो y और x भी मिल जाएगा according to these equations. The equations I mentioned here, according to these equations, if you know bz, you also know by and bx. मिल जाएगा easily. So that is why my whole idea is to find ez and bz, Because if I know Ez and Bz, I know all other four. And then I started finding this Ez and Bz. And first thing I'm doing is for TE waves, transverse electric wave. For transverse electric wave, Ez is 0, and only thing that is left to find is Bz. And Bz is a function of two parameters, x and y. Why? Because value of Bz at this point will be different. Value of Bz at this point will be different. Value of Bz at this point will be different. It is a function of x and y, but it is not a function of z. As your wave is going forward, at all the points, it will remain same. If the value is 10 here, then the value will be 10 here. If the value is 5 here, then the value will be 5 here. It only depends upon x, y, not on z. Because when your wave moves and it comes out on the other side, energy should remain same. Exactly same. Okay, good. So now let's do the maths, and this maths is very important, and you can try to do it with this, or you can look at it carefully. So I already told you, in order to find Ez and Bz, you need to use these two equations. Ez is already 0, so let's forget about this. So we need to solve this equation. So let's write it out. Curly square x by curly x square plus curly by curly y square plus omega by c square minus k square. Bz equals to 0. Now I put my Bz as xy. Now this xy means that this is some function of x and this is some function of y. This can be cos x, this can be sin y, this can be sin x, this can be cos y, something. This capital X means that you have some function of x. This capital Y means you have some function of y. You don't know what is a function, but you have some function. Don't confuse it with simple x and y. Don't confuse it with simple xy. This capital X means that you have some function of x. Capital Y means you have some function of y. So let's put our Bz as capital X, capital Y. If I put my Bz as capital X, capital Y, then here I will get xy. Since it is a derivative with x, I can keep my y common, and I will get curly square capital X by curly small x square. Again, I will also put my xy here. So since it is a derivative of y, so keep x common, and I get curly square capital Y by curly small y square. And then I can, this thing is constant, so let's write this as constant and multiply it with xy. So only thing that I have done is replace my Bz with xy. Now you divide the entire equation by xy. So what do you get? If I divide it by xy, I get 1 by x curly square x by curly x square. I will get 1 by y here into curly square y by curly x square. And then in the end, this xy gone. So this thing, I get this equation. Now here comes the another arrow in our game. Another arrow I am going to shoot. Number one arrow was write your Bz as capital X capital. The second arrow, and this thing is same for all. Whenever you use the method of separation of variables, you use the same steps. So the second step is that, what do you say is that this thing is also constant and this thing is also constant. Why I'm saying that? Why they both has to be constant? Why they cannot be variable? Anyone? Any guess? So what I'm trying to say is that this thing is also constant and this thing is also constant.
Because
Although it contains x and y. Yeah.
the first term is only a function of x and the second term is only a function of y, and they equal to some constant. So both of these terms must be constant.
Must be constant. Yes. So it maybe does not make sense to all of you. So let me try to put it in this way. So let's say I change the value of x in this equation. I change the value of x. So this equation will change, but this equation will not change. Right? So let's say this is my variable of x plus variable of y equals to, this thing is constant, so equals to some constant. So let's say I change the x, I change my x. So this will change, but this will not change, and this will also not change. How is this happening that this is changing, but other two are not changing? Is this possible? That in the three terms, only one term change and other two does not change. How can this happen? How can this happen? It cannot happen. Now let's reverse it. Let's say I change my y. So if I change my y and only this thing changes, because this is a function of x, so this will not change. Constant will also not change. Only this is changing. How is this happening? How will you satisfy your equation? Right. Let's say I am writing this equation 2 plus 4 equals to 6. And I change my x. So this 2 becomes 3. This thing did not change. This still remains 4. And this thing also does not change. This still remains 6. So 3 plus 4 is not 6. 3 plus 4 is 7. So I can have a happy solution or a acceptable solution only if this term and this term, both of them are constant. So they never change. You change x, you change y, you change whatever you want to change, but these two things will not change. Only then this equation will remain satisfied forever. For example, let's say I have 2 plus 4 equals to 6. Now I change the value of x. This 2 remains 2, this 4 remains 4, and this 6 remains 6. Still my equation is satisfied. I change my y, this 2 remains 2, 4 remains 4, 6 remains 6. My equation is still satisfied. But if this happens that I change my x and this 2 becomes 3 and other 2 did not change, gone. My equation is gone. So the only solution which is possible is that this is also constant and this is also constant. And just for namesake, I gave this constant as minus kx square, and I call this constant as minus ky square. I do this always. Whenever you use separation of variable, you have the same method to use. Whatever is constant, you call them as something, some constant. So we call this thing as minus kx square, and we call this thing as minus ky square. So what does your equation?
Sir,
Yeah, please. Yeah, please.
this kx and ky has nothing to do with the k in the third term. Like it is just a name, right? Like that case.
It has nothing to do with this. Yes, you are right. I'm not forcing you to find any relation between this and this, right? No relation. If it comes automatically, it's fine. But for now, we call this constant this and we call this. Okay. Although the dimensions have to be same, right? Because you know that you are adding the 4 terms, right? 1, 2, 3, 4. All the 4 should have the same dimension. So the dimension of this k square and this ky square will be same. Right? So I know that this is oranges ka square. That is why I call this as some oranges ka square. Understand? So if this is oranges, then this also has to be oranges. Only oranges can be added to oranges. So I knew that this has the units of oranges. That is why I called this as minus kx square, and I knew that this is also a unit of oranges, so I called it as minus ky square. That's all. Okay. Okay, fine. So I got two
Sir,
equations.
minus क्यों ले रहे हैं plus क्यों नहीं ले सकते जैसे minus
Because you know minus, but if I take plus, then this is not a simple harmonic equation. If I take minus, which equation is this? By looking at this equation, which equation do you see? Which is these equations? I expect this much. This is simple harmonic equations. So whenever you see some equation like this, d square y, or you see something like this, d square theta by dt square equals to minus omega square theta. Here also you can replace theta with x and t with small x. This equation and this equation are exactly same. Only some symbols are changed. So these are the equations of simple harmonic motion. Harmonic motion. Okay, so these are the equations of simple harmonic motion. So if I call this as minus kx square and I call this as minus ky square, so minus kx square minus ky square plus omega by c square minus k square gives you 0. And this is very important equation. You need to remember this. If you forget about all the steps, I am happy, I'm satisfied, I have no problem. But you cannot forget this equation. So please note this equation very carefully. This equation is extremely important. Okay. Okay. Now I got two equations. So let's solve them. So I will solve this. I will solve this. This is a simple harmonic equation, and the solution of simple harmonic can be two things. Either it can be sine kx or it can be cos kx. I'm not sure if it is sine or cos. So the general solution will be a sine kx plus b cos kx. So I call them as both. It's a general solution. If you have done even little bit of differential equation, you know that simple harmonic equation gives you two results: sine kx x and cos kx. That's all. And the general solution is a sine kx plus b cos kx. That's all. Okay. So this is my general solution. Now I'm going to use the boundary conditions. And my boundary conditions, as you already know, is that parallel component is 0, which means, sorry, perpendicular component is 0. So my bx is 0. So let me remind you about the boundary conditions. So your b perpendicular was 0. If I talk about this surface, then b perpendicular will be bx. And on this surface also, b perpendicular will be bx. Perpendicular to this surface is going along z axis, sorry, x axis. So bx has to be 0. Okay, so if bx has to be 0, let's go to the equation so that I can show you something. If bx has to be 0 and Ez is already 0, because TE wave Ez is already 0, then can I say that curly bz by curly x has to be 0? What do you say? Why, first of all, I'm saying that bx is 0? Because I have this surface, and I already told you that what is the boundary condition, that b perpendicular is 0. So what is the perpendicular to this surface? Perpendicular to this surface is bx. So bx has to be 0 on the boundaries, on the lower boundary and on the upper boundary. So if bx has to be 0 and Ez is already 0, because transverse electric Ez is already 0, can I say that curly bz by curly x is 0? What do you say? Only then this will be satisfied. What do you say? So curly bz by curly x has to be 0. And that is exactly what I'm going to use. I am going to say that curly bz by curly x has to be 0. Curly bz by curly x has to be 0. Yeah, please. Yeah, any doubt? Okay. And what is bz? Bz, how did I wrote bz? Bz I wrote as x comma y. Oh, sorry, x y. And since it is a derivative with x, you can take y common. bx 0. Yeah, please, sure, bx 0 क्यों हुआ? Let's see. हमने दो बाउंड्री कंडीशन समझे थे, हमने दो बाउंड्री कंडीशन समझे. पहला कौन सा था कि b परपेंडिकुलर 0 है. दूसरा कौन सा था कि e पैरेलल 0. अगर मैं इस सरफेस की बात करूं तो व्हाट इज अ परपेंडिकुलर कंपोनेंट? b का कौन सा परपेंडिकुलर, इसका किस डायरेक्शन में जा रहा है? इसका परपेंडिकुलर x डायरेक्शन में जा रहा है, और परपेंडिकुलर कंपोनेंट तो 0 होना चाहिए. सो bx इज 0. सो इफ bx इज 0, देन आई यूज दिस इक्वेशन. अगर bx 0 है and this thing is already 0, because Ez already 0, then curly bz by curly x is also 0. And bz I wrote it as x comma y, or since it's a derivative with x, तो y को बाहर लिख लेते. So take y outside. I am left with this curly capital X by small x equals to 0. अब मैंने कैपिटल X निकाला है ये. So my capital X is a sin kxx plus b cos kxx. Now let's take a derivative with x. Let's take a derivative with x. So I will get a cos kxx plus minus b sin kxx. So this is my derivative. So now I have two surfaces. One is the bottom surface, which is x comma 0, and one is a top surface, which is x comma a. So this is x0, this is xa. So I have two surfaces, x0, xa. So first use x0. If I use x0, cos 0 is 1, so I get a kx, and sin 0 is 0, so this is 0. So my a kx comes out to be 0. It means my a is 0. My a comes out to be 0. Similarly, at x equals to a, also my derivative is 0. If I put a here, so I get a is already 0, so this thing is already gone, so let's forget about that. एंड हेयर आई गेट माइनस बी के एक्स इंटू साइन के एक्स। एक्स को अब मुझे क्या पुट करना है, ए। ठीक है, तो पहले मैंने अपनी बाउंड्री कंडीशन लगाई एक्स इक्वल टू 0 पे, और फिर मैंने अपनी बाउंड्री कंडीशन लगाई एक्स इक्वल टू ए पे। जब मैंने बाउंड्री कंडीशन एक्स 0 पे लगाई तो ये चीज तो ऑलरेडी 0 है ही, वो तो हम बोल ही रहे हैं कि करली एक्स बाय करली एक्स हैज टू बी 0, वो तो हम बोल रहे हैं। सेकंड इज कि अगर मैं 0 पुट करता हूं, इफ आई रियली पुट इट माय 0, सो दिस थिंग विल बिकम 1, so I get a kx and this thing automatically goes to 0 because sin 0 is 0. So ये चीज मेरी 0 आ गई, it means a is 0, a 0 हो गया। if a is 0, then I apply my boundary condition at x equals to a, तो ये भी 0 है। and then this is a kx and this is cos kx in, sorry, cos kx into a, cos kx into a। ये तो 0 हो ही चुका है क्योंकि a ऑलरेडी 0 कर दिया है मैंने, तो इसको खत्म कर देते हैं। आई एम लेफ्ट विद इज दिस, सो आई गेट माइनस बी के एक्स इंटू साइन ऑफ के एक्स इंटू ए। अगर ये 0 है, इट बेसिकली मीन्स दैट साइन के एक्स इंटू ए इज ऑल्सो 0, ये चीज 0 होगी। तो साइन थीटा जब 0 होता है, व्हेन साइन थीटा इज 0, इट मींस थीटा इज इक्वल टू एन पाई, 0 पाई 2 पाई 3 पाई 4 पाई। साइन थीटा जब भी 0 होगा तो थीटा होगा एन पाई। So if sin kx into a is 0, it means kx into a is equals to n pi। और यहाँ m या n की वैल्यू जो है वो है 0 1 2 3 4 so on, एंड kx की वैल्यू आ रही है m pi by a, m pi by a। तो मेरा फाइनल x का सोल्यूशन क्या आ गया, माय फाइनल x सोल्यूशन कम्स आउट टू बी, a तो 0 हो गया, b है, cos kx की वैल्यू मैंने कितनी निकाली, m pi by a into x। किसी को सिमिलैरिटी दिखी? कैन एनीवन टेल मी द सिमिलैरिटी है, किसके साथ सिमिलैरिटी दिखी है? ये सोल्यूशन किसके जैसा लग रहा है? अभी तक आपने फिजिक्स में कुछ पढ़ा हो ऐसा, एनीथिंग, कोई आपको
Potential well,
सिमिलैरिटी?
sir.
पोटेंशियल वेल के साथ सिमिलैरिटी होगी, ट्राई टू सी। पोटेंशियल वेल में भी क्या होता है, व्हाट डू यू सी इन पोटेंशियल वेल? sin n pi x by a, cos n pi x by a। Here also we are getting the same thing. By the way, in the end of this lecture, I am going to tell you that all of this mathematics is just for understanding, not for remembering. अगर आप ये सारी मैथ्स भूल भी जाओगे तो तब भी मैं आपको 4 फॉर्मूला ऐसे बता के जाऊंगा जिससे आपके सारे वेवगाइड के क्वेश्चन हो जाएंगे। बट आई डोंट वांट टू स्किप द कॉन्सेप्ट, दैट इज व्हाई आई एम गोइंग थ्रू दिस डेरिवेशन। Usually I don't like to go through the derivations, but it's fine, we are going through it, and but in the end I will give you 4 formulas, everything will be done। Okay, good। Similarly, if you solve the equation for y axis, जैसे मैंने x को solve किया, you can also solve this equation। You will basically get, आपको ky क्या मिल जाएगा, ky will be n pi by b। x की डायमेंशंस थी a, सो वहां पे आया m pi by a। y का डायमेंशन है b, तो we got n pi by b, that's all। So we got this kx and ky। Okay, kx and ky cannot, why kx and y cannot be negative integers? You can put negative integers, कोई प्रॉब्लम नहीं। Negative and positive does not change anything here, that is why। Negative and positive का impact तब होता है when negative integer give you some other physics and positive integer give you some other physics। Here nothing will happen, negative integers will just start telling you that it is going in reverse direction। Okay, nothing else। So that is why it's not important, you can take it, no problem। Okay, yeah please, yeah। So then how does my solutions looks like? My x looks like some constant, वैसे तो मुझे इसको b लिखना चाहिए, a नहीं लिखना चाहिए, some constant into cos of m pi x by a, and इसमें some constant into cos of n pi y by b। बट ये मेरा फाइनल सोल्यूशन नहीं है, ये तो मेरा कैपिटल एक्स एंड कैपिटल वाई है। व्हाट इज माय फाइनल सोल्यूशन? माय बी जेड वाज इक्वल्स टू कैपिटल एक्स इंटू कैपिटल वाई, सो सम कांस्टेंट मल्टीप्लाई बाय cos of n pi x by a into cos of m pi y by b। This is the very important part। So let me give you the summary points of this। We started by saying that whenever the wave is inside the waveguide, electric field and magnetic field are no longer transverse। No, they are not transverse, they are longitudinal। they can also be, some component can also be along the longitudinal side. So if the wave is going along z-axis, then there are two longitudinal components. One is for electric field, Ez, and another is for magnetic field, Bz. Then we wrote four equations, Bx, By, Ex, Ey. And we said that if we know Ez and Bz, if you know Ez and Bz, you know all other four, Ex, Ey, Bx, By, so on. So our entire purpose is to find Ez and Bz. Then we started our calculation for rectangular pipe, and we said for rectangular pipe, x-axis is A, y-axis is B. For rectangular pipe, let's say TE wave. TE wave means transverse electric, so Ez becomes 0. So only thing that we are left is to find Bz. And when we did find a Bz, our Bz comes out to be B naught, some constant, cos n pi x by A into cos n pi y by B. Okay. And in this entire derivation, there are some steps to be remembered here. The number one formula to be remembered is this one. Very important. Number two, and in this formula, you will ask yourself that what is this omega, what is this k? Omega is the angular frequency of the wave. So let's say you are sending the wave with some frequency. K is the wave number of the wave. So you are sending the wave and it has some wave number. Kx and ky are constants. So this is the first equation. The second equation to remember is that what is kx? Kx is m pi by a, and what is ky? Ky is n pi by b. So three equations, and then the fourth equation to remember is this. If you remember these four equations, your work will be more or less done. There are many other as well, but these four are the important from this derivation. Now this kind of solution are known as the TEMN mode. For example, you might have seen TE11 mode, TE12 mode. What is this 11, 12 means? First thing means M and second thing means N. What is the value of M and what is the value of N? And they will be integers. Whenever we write our modes, A is our larger dimension and B is our smaller dimension. So you can ask yourself, which axis to take as x-axis and which axis to take as y-axis. कौन सी एक्सिस को A बोले, कौन सी को B बोले, कौन से साइड को A साइड बोले, कौन से को B बोले. So whatever is a bigger side is A and whatever is a smaller side is B. So we always say that first one is a bigger side and second one is a smaller side. TMN mode. Okay.
Sir,
First, yeah, please. Yeah.
sir, you wrote M with Y, but like if it is for A, then it should
Oh,
be
sorry.
like
Yeah,
M pi
thank you.
by.
Yeah, thank you. Yeah, thank you. Thank you for correcting. Yeah, thank you. Yeah. You are correct. I chose X for M and N for this. Yeah. So it is MN. We can now see MN. TEMN mode. Okay. Now some facts. Number one fact is TE00 cannot exist. Both M and N cannot be 0. Because if M and N both become 0, cos 0 is 1, sin cos 0 is 1. So your magnetic field will be constant. And if magnetic field become constant, can anyone tell me what will be the bigger problem if magnetic field becomes constant? Can magnetic field be constant? Yeah, please.
There's no induced electric field.
There is no wave.
Yeah.
There is no wave. What is electromagnetic wave? Magnetic field oscillating, electric field oscillating, both of them results into some wave. So if Bz becomes 0, the bigger problem here is that Bz is constant. So see, first of all, Ez was already 0. So this is gone, this is gone, this is gone, this is gone. Now if Bz is also constant, then this is also gone, this is also gone, this is also gone. Because if the Bz is constant, then their derivative will be 0. Derivative will be 0. So if this is 0, then everything is 0. Ex 0, Ey 0, Bx 0, By 0. So nothing, wave is not left anymore. You are not having a wave. You are just having a constant magnetic field. Okay. So that is why TE00 wave is not possible. You can never have TE00. At least one of the index has to be non-zero. One of the index has to be non-zero. Okay. Okay. Now another important equation. Now it's not something new. I'm just rewriting that. Yeah, please. Yeah. So I'm rewriting this equation. So if I rewrite this, I get k square equals to omega by c square minus kx square minus ky square. If I take under root on both sides, I get this. And then I also put my kx and ky value. So kx is m pi by a and ky is n pi by b. Very extremely important. Extremely important equation. I would say this is one of the most important. Because you can write first equation in this term. If you remember first, then you also remember this. If you remember 1, 2, 3 equation, then this also you remember. Nothing new here. So this is one of the most important equation you need to remember. Okay. So this is the possibility. This is also known as the dispersion relation. Any relation which is between k and omega is known as the dispersion relation. And this relation is between k and omega. Okay. And if you really want that your wave goes without any loss. So let me give you some tips about the electromagnetism. In electromagnetism, what happens? So in electromagnetism, number one, so let's say you have an EM wave. Let's say the frequency of EM wave is something 10 megahertz. Then omega is 2 pi by 2 pi f. And let's say the wavelength of the EM wave is 20 nanometer. Then the wave vector is 2 pi by lambda. So this is k and this is omega. This is known as angular frequency and this is known as wave number. If you, that is why I told you that before this lecture, you should go for the EM waves lecture, which I gave you. If you are a part of my course, that will be really helpful for you to watch the EM waves lecture. Very extremely important. Okay. Then comes another part of this. Now I have a very interesting question for you. We are done with the mathematics. We have solved for Bz. Bz comes out to be some constant cos of m pi x by a and sine of n pi y by b. Technically, we have solved our problem because we know Bz, we know Ez. Ez is 0. So if we know Bz and Ez, we also know other four. So we know our electric field, we know our magnetic. And we also know the relation between k and omega, which is also very important. Now the question is, will be asked like this. So let's say I have a guided wave. Can all the frequencies pass through this guided wave, or there is some cutoff that minimum this frequency should be there or maximum this frequency should be there? According to your guess, should there be any cutoff or any wave can pass through any waveguide? What is your guess? Should there be any cutoff frequency? I'm not saying that.
Yes, sir.
What is it? Just say yes, it should be. For every waveguide, there is a cutoff frequency.
So it should be like that omega by c square should be greater than this.
Perfect. Yes, perfect. And why is that cutoff frequency there? Because you don't want energy loss. You don't want energy loss. If your k is imaginary, then energy loss happens. And if your k is real, no energy loss happens. So if your wave number is positive, for example, if I say that e raised per iota kx, if your k is real, then it is e raised per iota kx. So it is oscillating wave. But if this k becomes imaginary, let's say iota k, then you get iota into iota k into x, which is basically e raised per minus kx, because iota square is minus. Now this is exponential decay. Exponential decay. So as long as your k is real, your wave is oscillating. No energy loss, wave is oscillating from one point to another. But the moment your k becomes imaginary, there will be an energy loss. And you do not want energy loss in your system. So only condition that you have to make sure, which satisfy always, is that your k remains real. If you want your k to remain real, then whatever is inside the under root should be positive. Because you know under root of negative numbers are imaginary. So whatever is inside the under root should be positive. So this thing should be bigger than this. So that is what I have written. Omega by c square should be written as greater than pi square m by a square. I have taken pi common. So pi square m by a square plus n by b square. So this is my condition. So by multiplying c square on other side, yes, I'm talking about the dispersion relation. So if I take my c square on other side and do the under root, I get my omega to be greater than pi c m by a square plus n by b square under root. This thing is known as omega mn. So my omega should be greater than omega mn. Otherwise, my frequency will not oscillate, my wave will not oscillate, and it will exponentially decay. Another important formula, and this formula is for the cutoff frequency. The formula for cutoff frequency is omega mn. Omega mn is given by pi c m by a square plus n by b square. A is the length, b is the breadth, pi you know, c you know, mn is a mode, 1 2 2 1 1 1 1 0, something like this, right? So this is the cutoff frequency. Minimum frequency, if your frequency is less than this, your wave will not exist. Your frequency has to be greater than this mn. Only then your wave can pass through. Your wave will travel through. If your frequency is less than this, then it is not allowed. So your wave frequency should always be greater than this frequency. Okay. So frequency less than this is not possible. Now I already told you that 0 0 is not possible. So what is the minimum which is possible? You tell me. 1 0 is the minimum or 0 1 is the minimum?
1 0.
1 0. Because if I put 1 0, let's say I put 1 0 here. So omega n become, so this thing will become 0. So I will get pi c by a. But if I put 0 1, I get pi c by b. And you already know a is greater than b. A is greater than b. So if a is greater than b, then this thing is small and this thing is large. So the smallest thing is omega 1 0, not 0 1. So the smallest mode means frequency. The smallest frequency or smallest mode is TE10. And if I put TE10, then my frequency comes out to be omega c by a. So my frequency should be greater than this frequency. Otherwise, my wave will not move through the waveguide and the energy loss will happen and it will decay. So this is also one of the important results. Okay, one of the important results. Two more important results, and then theory wise we will be almost over. Okay, I know the theories because I am covering all of them in one class. Waveguide is usually 3 or 4 lecture thing, but just one class I will end waveguide completely. Now just playing around, you already know k is this thing. Okay, now I can write my k in terms of omega n. So I already know this is my omega mn. I already know this is my omega mn. So nothing here to play here. So what I did is I took 1 by c common. So this becomes omega square and this thing will become omega nn square. So this is also one of the important relations, that k can also be written as 1 by c under root of omega square minus omega mn square. Omega mn you already know is a cutoff frequency. Okay. Another possible way to write is that you take omega common. If you take omega common, outside you get omega, and inside you get 1 minus omega mn square by omega square. So you just have to take omega square common. Here you will get 1, and here you will get omega square mn divided by omega square, and outside you get omega. So this is some ways to write it. So this is important. If you know this, you can easily write this. Right. Why I did this? Because I wanted to write two things. One of them is known as phase velocity. Phase velocity is basically with how fast electric field and magnetic field is oscillating. Phase velocity does not mean that how fast the wave is moving. Phase velocity means how fast the electric field and magnetic field is oscillating. And that is given by omega by k. And if you do omega by k, you already have this omega, you already have this k. If you do just divide both of them, you get c by 1 minus omega n by omega square under it. And as a matter of fact, this thing is greater than c, speed of light. Why? Because this thing is less than 1. So if this is less than 1, then this becomes greater than c. Greater than c basically means that your electric field and magnetic field are oscillating even faster than speed of light. But we don't care about that because those are not actually really what happening. That is something in your mathematics. Really what is happening is that how fast your wave is going from one place to another. Inside that wave, how fast the electric field and magnetic field is oscillating, that is a mathematical concept. Because electric field and magnetic field can oscillate. But our matter of fact is that how fast the wave is going from one point to another. So that is not phase velocity. That is group velocity. Group velocity means that at what speed the energy is carried from one place to another. That should not be greater than c, because otherwise relativity will fail. So group velocity says that group velocity is equals to d omega by dk, or reverse you can write dk by d omega. So if you just take the derivative of this thing, you already know this
So could
dk by
you please explain again phase velocity and group velocity difference, please again?
phase velocity means that your wave is going from one place to another. So it goes from one place to another with this group velocity. Group velocity. It goes from point A to point B with group velocity. But inside that wave, electric field and magnetic field is oscillating. They are oscillating with speed even greater than speed of light. Fine, we don't care. But the signal is not going from one place to another with phase velocity. Signal is going from one place to another with group velocity. The formula for phase velocity is omega divided by k. You already know k, you already know omega. So using this relation, you simply do d omega by k. And your group velocity is given by d omega by dk, or you can write 1 by dk by d. So you can do dk by d omega. So take a derivative of this. So if you take a derivative, I have done. Yeah, please.
So I'm saying so in the phase velocity itself, the electric field and magnetic field are vibrating at speed greater than the speed of light. So
Okay. So yes, it is. It is. Mathematically, it is. But it's not a problem. It is not breaking relativity. Relativity breaking will be that you go from one point to another with the speed greater than speed of light.
so the wave itself is traveling speed less than the speed of light, but the electric field and magnetic field itself inside, they are vibrating
Oscillate.
speed, oscillating
Yes.
more than the
Yes.
speed of light.
Yes. Yes.
So
Exactly.
then we call it as phase velocity, right, sir?
Nahi, then nahi. Phase velocity is a general definition. For in this case, we are getting those results. Okay. Phase velocity is the velocity with which your electric field and magnetic field oscillates. Sometimes it is c, sometimes it is less than c, sometimes it is greater than c. In this case, it is greater than c. Group velocity is a velocity with which the wave goes from one point to another. Right. In
Yes,
this
sir.
case, we are calculating. In all the cases, group velocity and phase velocity comes out to be different. For plane wave, it is different. For wave in a conductor, it is different. For this, it will be different. So if I do my d omega by dk, and if I put my values, I will get this result, which is c1 minus omega n by omega square. It is actually very simple to remember. It is basically c divided by under root of 1 minus omega n by omega square, and here you get c into 1 minus omega n by omega whole square. And this thing comes out to be less than 1, less than c, because this thing is less than 1. So this entire thing will become less than c. So your wave is not going from one place to another with the speed more than speed of light. It is going with the speed less than speed. So our relativity principles are okay. It's no problem is there. Okay. So that is what I have, right? So I will just do one question, and tomorrow I will be doing the CSIR net PYQs of this waveguide. So today I did the theory. You take time, you make the notes, you read the graphics. So what you have to do after this lecture, that has to be very clear, because I don't want to do the questions and you don't still remember the formula. That is bad. So today's homework should be that you go ahead. We will end the class. We will do problem also tomorrow. So what is your today's homework? Watch my lecture. You have already watched it. This is available. These notes will be made available to you. Okay. So you make your own notes. From these notes, make your own notes. And also make your formula sheet. That whatever formula I said are important, you write those down. And then you come up with those formula sheet tomorrow. And tomorrow we will do the problems based on this, so that you actually are able to anticipate the problems. And if you, I will be giving this PDF. This PDF already has all the problems. So if you want to try out the problems, that you can also try. It's up to you. But I will be doing these questions tomorrow in the class. And tomorrow we will end our waveguides. Okay? Usually it will take 2 days for each topic to be done. So 4 topics will take 8 days to be done. Okay? So that's all I wanted to talk about the theory of the waveguides. I hope it is clear. If you have any doubt, please let me know. Right?